Okay, so welcome everybody. Today I will talking about my new paper which is about dependency parsing, about improving dependency parsing. And as I have plenty time and maybe this research is not so big, I would like to present a short overview of my dissertation, and this would be something like the current update or the current status on my dissertation work. So firstly, I will talk about the relation extraction things, which is indeed the motivation for all the stuff about the dependency parsing. So in many areas of human activities, a large collection of unstructured documents form main information sources. For example, in legal domain, the text of laws or the court decisions, all of these documents are unstructured, and their efficient browsing and querying presents the main important things we want to work with such domains. The typical approaches to this searching in such collections of unstructured documents are full text search and metadata search, but in general both of these approaches do not use semantics, any meaning of this word. And therefore there was the project INTLib, which is an abbreviation from the Intelligent Library. It was a project funded by the Technology Agency of the Czech Republic. It ran from 2012 to 2015, and 3 partners cooperated on this project. It was our Institute of Formal and Applied Linguistics, it was Department of Software Architecture of our faculty, and the company Sysnet. And thanks to this project, we proposed and implemented a new approach to the search of unstructured documents. 3 main tasks was defined it, or 3 main tasks was our main topics of our research. The first one was to propose or to find out proper semantic interpretation of documents, of unstructured documents. Then we should find a suitable database engine and query language for querying our such collections of unstructured documents with some semantic interpretation or representation. And in the end, user-friendly browsing and querying, or we implemented an application which was user-friendly and I know for browsing and querying such collections. This task was the main domain for our institute. It was the proposal for a new semantic interpretation of documents or unstructured documents, and we implemented it using the knowledge base. We defined it as a set of entities and relations between them, and the real system which was implemented for obtaining such knowledge bases of unstructured document was the system Extractor, which is abbreviation from the Relation Extractor, and it is our final system for this task. The Extractor, so it extracts entities and relations from plain text. It has a server architecture, which means that if some clients has a document, has a structured document who want to process by our system, he don't need to install everyone, but to install anything, he simply requests the server with the unstructured document through the REST API, and the server process everything and returns the identified entities and relations, which is in fact the knowledge base of the document. We also implemented a web interface for the system, mainly for demonstrations. Here you can see the logo of the system, and on this side you can play with Extractor. There offers two extraction strategies, one for Czech and one for English plain text. Okay, so this is the main ideas about the system. For extracting entities and relations, queries over dependencies trees are used. and the system as a whole is proposed to be domain and language independent. However, there was just one real use case which was defined by the project Untitled Library, and it was the processing of Czech legal text or Czech legal domain. And to be more specific, we extract definitions, rights, and obligations from Czech laws in the end. So one concrete or one specific extraction strategy was implemented for Czech law documents, and in addition, we also add the English extraction strategy to be more demonstrative, to provide the system more demonstrative also for English-speaking audience. To evaluate the system, we manually annotated some legal documents, and we created the Czech Legal Text Treebank, currently in the version 1.0. It contains two documents. The first one is an accounting act, and the second one is the decree on double entry accounting for undertakers, which is in total more than 1,100 manually annotated dependency trees, which present more than 35,000 of tokens. The text was firstly automatically parsed, and then each sentence was manually checked and corrected. The whole tree bank is available through our Lin.Clarin service, and it is free for use for non-commercial purposes. And we introduced the tree bank on the LREC in Portorož this year. From the evaluation of the system, we also, in addition to the standard evaluation of the system, we also provide some error analysis, and the result was that 60% of errors was caused by improper dependency tree in the input of the entities extraction and relation detection. And this is our real motivation why we tried to improve dependency parsing, because that give us some change how to reduce the most errors which was caused during the extraction scenario or extraction strategy. We used, or the Restructor currently use the standard MST parser, which was defined by McDonald, Pereira, Ribaro, and Jan Hajic in 2005. It was trained on newspaper text. It means that it was trained on standard PDT 2.0, and as I know, the MST model was trained by Zdeněk Zabokarský, and there are also some adaptations, especially for Czech or only for Czech. And for this parser, long sentences, which are typical for legal text, are still problematic. Here is the evidence of all my things. Here is the evaluation of the parser on different sentence or on sentences with different lengths. You can here see in this plot that the parser is most success on sentences which has from 1 up to 10 tokens. The score, unlabeled attachment score, is higher than 90%. But if we add more tokens to the sentence, the score rapidly decreases. For example, here are sentences which have more than 50 tokens, and the score is under 75% of unlabeled adjustment score. 3 different bars for each group means different evaluation sets. The red bar means PDT D-test, blue one is PDT evaluation test, and the yellow one is Czech Academic Corpus 2.0. So what we should do, or what we can do with long sentences, maybe the most simple, or maybe the first idea is let's split them into smaller parts. This is not a new idea. Already Dr. Kubon in her dissertation in 2001 proposed to segment complex sentences into segments, which he defined as easily detectable and linguistically motivated units, which may be back combined into clauses, and clauses may be combined back into sentences. And using such segmentation, he proposed how to provide a structure of complex sentence with regard to the mutual relationship of individual clauses. This work was then improved by Dr. Kolopatkova and Dr. Holland in 2009. He proposed exact definition of so-called segmentation charts, which represent relationships among segments, especially relation of coordination, opposition, and subordination. And they propose a new module which should be put between morphological and syntactic analysis, which firstly determine the overall sentence structure, and then syntactic analysis should have a little bit easier task for the parser, because there are not so many tokens. Okay, a little example, which is really simple because there are only two segments. So let's assume the input sentence: s tím byly trochu problémy, protože starosta v řeči rád zdůrazňoval své vzdělání. The first thing is we should split sentence into segments. So Dr. Kolopatkova and Holland propose some easy rule-based algorithms to identify boundaries between segments. In our case, it was the punctuation marks, coordination, conjunction, brackets, and so on. So in our input sentence, there are two boundaries. This one is the first boundary, and this final stop is the second boundary. And after applying these rules, the sentence is split into segments. The first segment is s tím byly trochu problémy, then the boundary, comma, and then the second segment, protože starosta ve své řeči vzdělání, and final stop. And then after this step, the second thing on their proposal is to determine mutual relationships between segments. So this is also done by manually designed rules. The most important signals for its appearance of finite verb, appearance of subordinated expression at the beginning of segments, or some brackets. So in our case, these segments do not start with subordinating expression. There is a finite verb, and in opposite, this segment starts with some subordination expressions, protože, and therefore the overall relationship is here. This segment is subordinated to this main segment. Okay, and the last step in the algorithm is how to capture the layer of embedding for individual segment. So in this is very easy, because the main segment has layer of embedding equal to 0, and this segment, as is this subordinated to this, we would have the layer of embedding equal to 1. So the final segmentation chart looks like this. We simply defined different layers, and each segment obtain its layer of embedding. Here are 4 principles which are beyond to segmentation charts. The first one: main segments belong to layer 0. Then segments that depend on a segment on layer key belong to layer key plus 1. Coordinated segments have the same layer, and in the end, segments in parentheses, brackets, and so on belong to the k plus 1 layer, in comparison with some neighbors or the previous segment. Okay, so this was the segmentation chart, and Lopatkova and other colleagues also introduced some manually annotated data. In 2012, the group annotated more than 2060 or almost 2,700 annotated sentences, where the concept of segments was exploited. And in addition, not only the layer of embedding per its segments was defined, but also segments was joined back into clauses. So the final thing which was done was for each sentence, the result was the sentence clause structure, not the sentence segmentation structure. This work was also done automatically. Kruza and Kuboň in 2014 introduced automatic procedure for recognizing clauses and their mutual relationship, and the input was a plain text. In details, they used MST parser, but the nodes in the chart was not tokens, individual tokens, but the whole clauses, and they proposed that the MST trained on these structures would produce the final sentence clause structure as a closed dependency tree. And Honza Popelka in 2013 provide or implemented an automatic procedure for recognizing clauses and their mutual relationships back from gold standard dependency trees. This procedure was also used to annotate the whole PDT, and PDT I think from version 2.5, but definitely from version 3.0 contains also a clause annotation. And this clause annotation in PDT looks like this. So you can see that individual clauses are separated by colors, the colors of nodes and colors of arcs. So for example, this one is one clause, and this is probably main clause in green. The subordinated clause is in orange, red, and blue. So the things which we done after this previous related work was we used the analogy of segmentation charts, and we defined clause charts as this is probably the better sentence parts which we should work on it. So we take the definitions from Lopatkova and Holland in 2009, and in fact there are just two differences. There are three differences. The first one is that we simply replace the word segments to clause, and then two more differences are that subordinated conjunction at the beginning of each clause are considered as boundaries. So we exclude such expression from the clause. And the second one is if there are clause which was split into two parts, because is it common, or is it could be in the PDT, for example by an embedding clause, we consider it as two different clauses. We don't identify if there are splitted clauses, but we simply work with it as two different clauses. Okay, and here is the example of our clause chart. So this is the input sentence, while failure is usually an on-farm. The success tends to have many fathers, claiming eagerly that particularly they were present at its conception. So you can see that there are four clauses. The main clause is the success tends to have many fathers. The subordinated clause is failure is usually an on-farm. The subordinating expression while is excluded as a separate boundary at the beginning of the clause. the beginning of the sentence, and there are two more different clauses. So this is the final clause chart. The layer of embedding is here, and here is the linear representation of such clause chart. So if we define such clause chart, our first thing is how to create them, or how to generate such chart from the PDT. In fact, it is very simple, because as on the input we obtain the gold standard dependency trees with the clause annotation, and so the clauses are already identified, and the last thing which we should do is to determine a layer of embedding for each clause. And this is very simple, because the number of different clauses on the path from the class to the root in the dependency tree is in fact the layer of embedding. Here it will be really simple to see it. Let's assume such sentence. Ačkoliv jsou si jistí, že se jim podařilo rozdělit molekuly dekarbonu na části, nepodařilo se zmíněným vědcům zatím určit, jaké produkty přitom vznikly. Here is the sentence, or here's the dependency tree from the PDT with identifies clauses, different clauses, and we simply go linearly from the first clause to the last one. So the segmentation chart would have 4 columns, as there are 4 clauses, and the spoiler is that there are 3 different layers embedding, because there is this structure. So to determine the exact number or the exact layer of embedding for this, the first clause, we simply start with any node from this clause. So for example, the root one, and we go to the root and simply count the different clauses on the path. So we start here, we got here, and there is another, there is the different clause, so we count the first one. Here is the root, so the layer of embedding is just 1, because there is just one different clause on the path to the root. The second one, also the same algorithm, start here. Here is the first different clause and the second different clause. So the layer of embedding is 2. This one has no different clause to the path to the roof, so the layer of embedding is 0, and this is the main clause on the sentence. And this one is, this clause is subordinated to the main clause, so the layer of embedding is 1. So here is the different, here is the final clause chart, and the last thing which we should do is exclude subordinated expressions from the clauses. So we exclude the words ačkoliv and že and put them as boundaries. So the final clause chart is here. This is the linear representation. There is some boundary, then the clause on the layer of embedding 1, another boundary, comma, and že, then the clause on the layer of embedding 2, boundary, main clause on the layer 0, boundary, subordinated clause, and boundary. Okay, so once we have such clause chart, we could explore the whole tree bank and look on different clause charts. So here is the distribution, or here is the 5 top frequent, most frequent clause charts in the PDT and in the Czech academic corpus. So you can see that the first one, or the most frequent, is sentences with clause chart 0, which means that there is only one clause, and obviously the layer of embedding is 0 because there is no embedding. And here you can see this crosses presents the relative frequency. So we can here, and here is the correct axis for this curve. So we can here see that there is more than half portion of the whole tree bank consists just from the simple sentences. Then the second most frequent structure is 0B1, which means that there is one main clause and one subordinated clause, and such sentences is or represents about 15% of the whole data. Then there is a coordination of two main clauses, 0b0. Then there is a coordination of two main clauses, but one of the clause is also subordinated clause. So it's 0, 1, 0. And the last most frequent structure is a sequence of subordinated clauses, which means 0, 1, 2. And here is the parser score or the parser performance of different clause chart. To be complete, I add also the PDT train test, but there is no surprise that the score is higher because the MST was trained on this data set. So the red one is also PDT test. I'm sorry. The blue one is PDT evaluation test, and the last one, the yellow one, is Czech academic corpus. So the first interesting thing is if you look on scores achieved on the simple sentences and scores achieved on the sentences where is one subordination clause, the performance is better on this structure, which is a little bit surprising, at least for me. Another surprise is that coordination of two main clauses is also harder for the parser than the subordination. And the last surprise is that that score our maybe the most or the hardest structure is the best. Sure.
Was the score about all dependencies in the tree or just relation between clauses?
Whole dependencies. So I simply calculate or summed all dependencies from the sentence that belong to the. Yeah. Okay. Then just for the curiosities, in the PDT we have sentence with 36 clauses. And we have also a sentence with 7 layers of embedding. So their clause charts look like this one. It's a big sequence of subordination. Okay, so now I introduce you our clause chart parsing. It's our algorithm how to use such clause chart for improvement of dependency parsing. Several notes before I introduce the algorithms. The first one is we didn't train a new parser. We simply reuse the existing parser, which was trained on the PDT train test and was trained on complete sentences. So we use such parser as a black box and just try to give him or try to give it more simple parts or more simple sequences of tokens. The second note is that for now we exploit gold standard clause charts. We do not have automatic procedure which produce clause charts from the plain text. We took the gold standard dependency trees with clause annotation and generate the clause chart. And the second thing is that this work was published already on the ACL on the student research workshop session this year. So we try to improve the parsing using such information which is encoded in the clause chart, and we propose finally two different strategies, one for parsing coordinated clauses and one for parsing subordinated clauses. So let's start with the coordination. So first thing which we did was look on the most simple coordinated clauses. I mean the sentences which follows which have the clause chart 0b0. And the first thing which we did was compared the accuracy or the performance of the parser when it parsed the fulls, or when he parsed full sentences, I mean a full scale, or just individual clauses. And we can see that the improvement of the parser when he parses only individual clauses from such coordination is more than 4% of unlabeled attachment score. So this is a big space for improvement. The only thing is that we should handle in some way. So we could parse each clause individually, and then we should have just some strategy how to merge them back into one dependency tree, and we could obtain more than 4% of improvement. And our final strategy how to do it is here. And it is also generalized to the more than two coordinated clauses, but for more coordinated clauses. So let's assume that we have a sequence of coordinated clauses. They should have been neighbor clauses. And from the definition of the clause chart, it means that they are on the same layer. Our algorithm proposes that we parse each clause individually, and for each clause obtain its dependency tree. So for clause CI, we obtain dependency tree TEI with root node RI. And then we create a sequence of tokens where from each clause we took just the root node and merged them with the original boundaries from the sentence. So we create a new sequence of tokens, which is subsequently parsed by the MST parser to obtain a new dependency tree TS. And the last thing is the building of the original dependency tree or the final dependency tree. And this is very simple because we simply replace tokens Ri from this dependency tree and replace them by the full dependency tree which Ti, which we have already parsed. For example, let's assume the most simple case where there are two different clauses. John loves Mary, Linda hates Peter. So in the first step, clauses are parsed individually. The root node is verb, of course. So for clause 1, it's the verb loves, and for clause 2 is the verb hates. And then we create such sequence of tokens, loves and hates, which is then subsequently parsed by the MST parser, and in the end, loves and hates, respectively, loves is replaced by the whole dependency tree from T1, and hates is replaced by dependency tree T2. And here is the results of our experiment. So here is the full-scale parsing, or here is our baseline, the performance of the parser or the full sentences or the sentence with original tokens. Here is the result. Here is the performance of the parser when we parse only clauses and we remove the coordination between them. And here is the results of our approach, where is in fact improvement on 1.4% of UAS in average for different evaluation tests sets. Okay, so the last thing is parsing of subordinated clauses. Analogously to the previous example, we explored the most simple case, which is the sequence 0B1. Here you can see that there is also no improvement when we parse individual clauses. Here is the parser performance on the standard or on the full sentence, and here is when we simply remove the coordinated expression between these clauses and parse these clauses individually. So almost no improvement in this case. And the second thing is this is the comparison from the beginning, when you can see that the parser behaves better on subordinated sequences than on the simple sentences. So both things moved us to such proposal, which is our strategy how to handle with subordinated clauses. And our strategy is, in fact, leave it as it is. So if we had a sequence of subordinated neighboring clauses, C1 to Cn, where each of the clause must be on the deepest layer of embedding as the previous one, we simply create a sequence of tokens which is, in fact, all tokens from all clauses, which are back joined or merged by the boundaries between them, and we parse it as it is. So such strategy will have the same performance on the 0B1 sentences, and the first effect, or here is the first structure where it should have or would have some effect. And it is the coordination of two main clauses, and one clause is subordinate. One main clause subordinates another clause. And the strategy for parsing this sentence was firstly parse 0B1 as it is, and then you obtain 0B0 clause chart after parsing of this structure, and on them we can apply our previous strategy for parsing coordinations. And here is the result. The improvement of such strategy is 1.6% of unlabeled attachment score. So this was the strategy how to handle subordinations and coordinations, and the last things is something like meta algorithm or algorithm how to parse the full case parsings. And our strategy is work in cycles. In each cycle, look on the clause chart and check the deepest layer. If there are two coordinated clauses, which means that on the deepest layer there are two neighboring clauses, we can apply 0B0 strategy, and in fact the clause chart changes in so way that coordinated clauses are removed and it is replaced by one clause or one structure. And then, or in case that there is no such coordinated clauses on the deepest layer, there must be some sequence of subordinated clauses which where the deepest layer or the clause on the deepest layer is member of such sequence. And then we can apply our 0B1 strategy or our strategy for processing subordinated clauses. And after applying such strategy, the deepest layer is removed because the clause is embedded to do one token RY in effect. And because this cases is still not, or these cases still do not cover the whole cases which could have appear, we also had some simple fallback when there is no way how to deal with the given or with the current clause chart. We simply use fallback and it is standard full-scale parsing. We simply merge everything back to the one sequence and parse it as it is. And here is our final evaluation on the whole PDT, but excluded simple sentences. And we can see that in average there was 1% of gross improvement in average on each evaluation set. And if we include the simple sentences, the improvement is not so large, but there is still improvement 0.7 of unlabeled attachment score. So there are many things what we should do as our future work. The first one is we definitely have to evaluate this approach on Czech legal text treebank, as such treebank consists sentences which are in average twice as long as the PDT sentences. So I hope or I believe that improvement will be higher on such sentences. And the second thing in the evaluation task is evaluate it eccentrically using the task of relation extraction in extractor. So we implement a new parsing strategy to the restructure and provide another cycle of evaluation, and we hope that there will be improvement, and especially that the number of errors which was caused by the improper dependency parser or improper input dependency tree will be lower. The second thing, which is that important for us if we want to apply this strategy to the general sentences, is generate close chart from the plain text. As I already told, currently we use gold standard chart, so this is really neat if we want to apply this widely on the all sentences. And in the second in the last point, we believe that we could train special parsers, which was trained, for example, on individual clauses and so on, and which would be trained to parse the special cases during the parsing algorithm. For example, only subordinated clauses or whatever. So today I told you that sentence clause structure helps with dependency parsing, and our increase of unlabeled attachment score on PDT is about 1%. One disappointing things about this is that in a real parsing task, we should provide automatically detected close charts, and therefore if the algorithm remains as it is, but we simply replace the close chart to be automatically detected from the plain text, the increase of the improvement will be lower. However, we can train special clause based parsers, and which could improve the parsings of individual clauses. And the second thing is that we still have many times how to implement something better. but this is okay. So that's all. Thank you very much, and I'm looking forward for your questions.
I think I have a couple of questions and comments. The most important probably is your red emoticon over there. I'm a bit skeptical about what will happen when you really try to detect automatically the close boundaries, because I would fear that most of the improvements that you get now are from getting the correct boundaries between coordinate clauses versus coordination of anything else, which in my opinion would be the most difficult part to really, when you see a coordinating conjunction, to know whether it coordinates clauses or just something smaller
Definitely.
somewhere. So yeah, I guess you don't have any estimate of the accuracy right now.
So far, no.
Okay, so good luck with that.
Thank you.
And one minor point I had with the 0B1 B0 block, where you essentially have coordination and a subordinate clause in between. You're assuming that the subordinated part always depends on the first conjunct, which I would agree is the more probable interpretation, but definitely is not always true. So don't you think that sometimes it hurts actually?
Definitely sometimes it hurts, but however in total it hurts so much, and I already propose something better than close charts, and this is something from the beginning. It is the this one. The dependence, the structures where there is the clear information that some clause depends on another. And my work version is that there are clause trees, and such issues are then solved because I will have the knowledge that that some coordinated clause depends on which minor clause.
Okay, thanks.
How do you cope with commas? Dan Zemmer referred to conjunctions, but I think commas, as they are polyfunctional. So I'm asking you how you treat them. Because, you know, the commas can split conjuncts and coordinated structures, and also, of course, clauses.
Yeah. I think it is the same case as the coordinated conjunctions. So so far we have the gold standard structures. So we know that some commas are included in some clause as the coordination of clause members, or sentence members. But in the future, this is still open issue how I will handle in these cases. But from my current work, I proposed some classifier which look on the contents of each comma and simply classify it if it is the split, if such comma splits clauses or it is part of some coordination in the clause.
It would be quite good, I think, if you showed us more complicated compound sentences. You've just shown us the very transparent and simple
Definitely,
structures. Yes. You know, so I'd like to see how you would go with these complex structures. You know?
Definitely, I will present it if I will have it.
Understand well, so I am wondering whether parentheses should be every time treated as embedded subordinated clauses, because many times it can be also interpreted as opposition, for instance. So it's always on the lower level as.
Yeah, it's in fact oppositions are also handled as embedded things. So each parenthesis or each parenthesis embeds our clause to the deepest layer.
But sometimes it can be also oppositions.
Definitely yes, but in total, or if you look on frequencies, this is not issue for me now.
I think the problem is actually not in the label, whether you say it's apposition or not, but here the main point is the strategy, that the parser will not be allowed to go beyond the parentheses, so that it doesn't mess up things beyond limits.
What about the split clauses? Isn't it an oversimplification if you treat individual parts of such clauses as
different
individual clauses? Yeah.
For now, I didn't handle it in a special way, because split clauses is also not so frequent that it influence to the final score in some important way. So
typical a noun is followed by a relative clause, and then the sentence continues. That the main clause continues. So do you treat such compound sentences
so far, no,
as three
but
parts or just two parts? Three parts, huh?
Three different clauses.
Yes,
Yeah.
Uh-huh.
So just to add to this, you don't really need the segments that you call clauses to be real clauses in order for the parser to improve.
Definitely,
right?
yeah.
Because in this case, I think with the embedded sentence, the first half is like parsable on its own, and the second will usually be parsable as well. I mean, you might miss some edges, but on the whole, you're not going to miss a lot of them. But this would be my question, because what using gold standard clauses essentially does is that in the MST parser, it fixes a hard zero on some subset of the edges in the complete graph.
Mm-hmm.
And looking at the improvements overall, did you actually have a count of like how many % of edges you are affecting in this way? Like if you segment the data into clauses, is the improvement larger than you would expect simply from the fact of having gold standard segmentation?
Yeah, good point, and I don't have such numbers so far. So another to do to my future work.
Thanks.
One more comment. I would really encourage you to try other parsers too, because there are sometimes huge differences in what kind of errors individual parsers do. So you might get completely different picture.
Okay.
Thank you very much for your interesting talk, and let me remind you that next Monday, Ted Sanders is going to talk on discourse analysis. It's a foreign speaker from Utrecht University, and it's the lecture delivered from Fraternium Sanders. So you are all